We'll start with automate to dominate, supercharging network provisioning at Meta. I'd like to welcome Kang Xi to the Nanox stage. Kang is a network engineer and tech lead at Meta, where he has been driving major projects in network provisioning and delivery. His expertise spans multiple areas, including modeling, automation, reliability, and new product introduction. Before joining Meta, Kang had a diverse career that included positions as an engineer at Google X, ONAP, and AT&T, as well as a faculty at New York University. Welcome, Kang.
Thank you. Sure, this works. Great, thank you for the introduction. First time at Nano giving a talk, this is so exciting. And even more exciting, this is Tuesday afternoon. We still have a lot of people in the room. Thanks a lot. My name is Kang. I'm a network engineer working on backbone provisioning and delivery in Meta. So I'll talk about our story of provisioning automation. So the work is really done by a great team in Meta. I'm just a communicator here, which means, if you have easy questions, feel free to ask me. If you have tough ones, look around. You're going to find a lot of people wearing this T-shirt. Automate to dominate. Ask them. They're my colleagues. They are smarter. So let's get started. I'll start by talking about the concepts, right? What we care about, what we want to achieve. And then following that, some fundamental principles we follow to make our life easier. And what does it take to really execute a provisioning automation? And after that, we're going to talk about the big picture at high level, what provisioning automation means at Meta. And then we're going to use a case study to drill down to the details, and hopefully some of the concepts, components, processes, and designs will be more clear and concrete. So to start, we know that provisioning is a very heavily overloaded word. So is automation. So what does it mean? At bare minimum, provisioning, we can say it is as simple as adding a new device to the production and let it take traffic. So we can say you grab a new device, install the device, hardware, connect the cables, make sure that you update the software to the desired version, apply desired configuration, and double check everything, pass all the audits, and then we can undrain the device to take traffic. So this seems pretty straightforward, certainly is nothing unusual. But what is more challenging when we're talking about scale? Scale doesn't mean we have to reach a hyperscale as Meta. With a few hundred devices, it can kill us if we follow a manual process, rely on tribal knowledge to provision and maintain the network. We have to employ automation, right? So moving on, what we really do using automation, automated provisioning. Provisioning, the mission actually covers end-to-end throughout device lifecycle management. It involves modeling, it involves data, and it involves a lot of tooling. So device lifecycle management, right? When we have a new device, in order to put this into production, we have to do installation, cabling, racking, and after that, we're going to do bootstrapping, adding a minimal configuration to the device so that we can reach the device and do all kinds of inspection and verification. After that, we do software update. We apply the desired configuration, and then it starts to take traffic. However, the network system is not a static system, it's dynamic. We have to maintain the network continuously. So throughout the life cycle, while the device is in production, in use, we're gonna have to update the software, we're gonna have to update the configuration. So our colleagues this morning talked about 1 million maintenance per year, right? It could be even more in the future. So until at some point we're gonna take it off the fleet to decommission the device. So there are a lot of touch points, and the provisioning covers a lot of those touch points. So now let's focus on our goals, what we really want to achieve. The bare minimum, all the ultimate goal of provisioning is to add capacity. We want to deliver capacity as much as fast as possible, right, based on business requirement. However, that is not the single goal we want to achieve. Together with that, there are a few other things we have to consider, right? We want to do things in a reliable way. Not only mean that we want to execute provisioning and deliver capacity in a reliable way throughout the process, it also means that whatever device we add to the production, we want to make sure that it is in good condition. The cabling are correct. The software is correct. The configuration is desired. All the health checks have passed. And this lays the foundation for a reliable fleet in operation, right? So sometimes even a simple mistake could mean a landmine. For instance, if there's a miscable, and it's still past traffic, but it's different from what we recorded in the database, then at some point it may give us troubles to maintenance, right? And the second part is also we care about scalability, right? We're solving today's problem, but we're talking about, we have to think about what we need in the future, tomorrow, next month, next year, right? So for a large scale network, oftentimes we have to deal with multiple vendors. We have to deal with a variety of device roles. They're doing different things, they function differently. And talking about scale, it's not only the quantity of the devices, it is also the variety of features we have to support. So all this needs to sustain our growth for years to come. And following that, we care about automation. So we talked about the reliability, we talked about the scalability, and a few other things. And how do we solve that? Automation is probably the fundamental choice to conquer all these hurdles, right? With automation, we can transform a process into a collection of code and tools so that we can minimize or even avoid human intervention. And this makes things more efficient, more reliable, and our processes become more deterministic, right? So moving on, we can say, how do you do this? But before we talk about specifically what technologies we use, what designs we have, we need to take a step back and think about engineering, right? Getting something done versus getting something done with engineering excellence are not always the same. So the second needs more thinking, needs more rigorous planning, needs probably some principles. So I can share a little story about myself. So a few years ago, I was doing a certain process, and it was manual. I said, okay, this is not very efficient. So we can automate this. So I wrote a little script, and it worked out well. And then following that, in the next few weeks and months, I discovered other features needed, so keep adding those features to the script and inflated it to be a quite sizable software a few thousand lines of code, right? And this is pretty common journey people take. But then at some point, it started to give me troubles. Even though shamelessly I say I'm an okay engineer, my code quality is not that bad. But at some point I find it was no longer very easy to add features to that piece of code. Things to get convoluted, right? And then at some point I say, okay, we have to start over again and refactor the code, right? So you may say, hey, Tom, this is an amazing story, right? How come you did things so stupid and still didn't get fired by Meta? Might be a good story. Ask question to my managers. They're sitting over there wearing this T-shirt. But the secret is all this happened before I joined Meta. So, but I'm not going to share my stupid stories while being in Meta. So there are a few things that didn't work out well in this story, right? This is not the entire picture of automation. At most, I would say this only touches the part that we do codification, transform a process into code. But it's not equal to automation. So I didn't think about modeling. I didn't think about the efficient way of maintaining my data. I didn't think about the future requirements. I didn't think about the growing and scalability of the software design, right? It's more of everything starts in an ad hoc way, and we start to add features in an ad hoc way. So that is guaranteed to fail at some point when the scale kicks in, right? So now we're looking at principles. I'm sure that when it comes to automation, when it comes to provisioning, there are more principles we care about. But here we list the 3 top ones that we adopt at Meta. The first one is single source of truth, which means we maintain data in a single place and let all the consumers consume the data from this single place. It's very straightforward, but in practice, it is not uncommon to see that folks may deviate from this. We may say, hey, it's convenient to create a duplicate of this data and park it somewhere else. Or it's convenient to derive certain data from a bunch of raw data, source of truth, and park somewhere. So it's very good for the consumers. However, convenience, in most cases, is not a strong justification to do something away from single source of truth, right? So oftentimes, I would say, stick to single source of truth, give us long-term benefit. Second part is model-based data. A lot of the processes, a lot of the designs are operations are data-driven. So model-based data, meaning that we design a schema. We represent the data in a rigorous way, in a strictly defined way, structured way, right? And certainly this does not come for free. There's an overhead in that. How do we design the schema? We maintain the schema. We park the data in a database, etc. Right? So certainly hard code the data in your code. In your code, sometimes it's much faster. It's easier to land, faster to land. However, in the long term, again, it's very possible that today we only have one consumer of that piece of data, but 6 months from now, turns out we have 5 consumers, right? And then having a model-based data will facilitate everything, will build a solid foundation for your ecosystem. Now, we're not targeting only one consumer, we're targeting an ecosystem. So talking about ecosystem, that is the third part, we want to consider unified tooling, right? So automation doesn't mean we're focusing on one or just a handful of features and we write a script to codify that. Instead, we need to think about today we have this business requirement, we have this bunch of features that we want to deliver, but what about tomorrow? What about the future, right? Today we're only providing one service, in the future could be 10, could be even more. And then from that perspective, our goal is not to build only one piece of software to deliver this function to meet this business requirement. Instead, we should think about the framework, the ecosystem that we want to build so that when we develop software, then it is modularized. The components can be reused. And the dependency among all these components, among all these tools, are clear and rigorously defined. So that in the future, even though all these tools may be owned, maintained, operated by different parties, you know, we can minimize potential conflict problems. We can minimize the landmines and gaps, right? And all these are very critical to provisioning, especially when it comes to automation of provisioning. So again, they do not come for free. We have to pay a price upfront, but long term, it's very rewarding to adopt all these principles. Now the question might be, seriously, these are the principles, but what does it take to do provisioning automation? I have components here. You may say, oh my God, a laundry list, right? It's not friendly. Reading through this laundry list is probably a perfect recipe for a nap at this time. But honestly, if you find this list to be sort of painful or at least annoying, picture this. This is really what we do. We have to actually transform this list into a collection of models, data, code, workflows, documents, and processes. And that is how we get things done, right? If this list is painful, the real work is probably even more painful, more challenging, right? But the good news is I'm not going to walk through this list. The thing is, if we randomly put things together as a long list, it is hugely challenging. It is a huge pain. However, if we adopt the principles, we take a structured way of automation, then this list can be organized in a structured way. And then it is much easier to understand, to consume the concept. It also greatly facilitates the design, development, maintenance, and operation of all these tools, right? So shortly, we're gonna look at all these components in a different way. Now let's look at the big picture, right? How we do provisioning, automation, and Meta, and why. So Meta operates one of the largest networks. So our infrastructure is gigantic. We have backbone, we have edge, data center, and the infrastructure network. And naturally, to construct such a huge infrastructure, we work closely with multiple vendors. And we certainly have a variety of device roles. Accordingly, we develop multiple models for all these devices. So the scale is certainly about the quantity. We have a large number of devices. It is also about the volume of operations. On a regular basis, we do a lot of new device onboarding to deliver capacity. We do a number of migrations because things change, designs evolve. And we certainly do decommissioning as well. To get all this large volume work done, automation is crucial, right? So if we try to understand the provisioning at the big picture in the end-to-end way, where does it sit in the product life cycle? So at high level, we can say a product, the life cycle looks like this. At the very beginning, we have a new business requirement. Then we scope the new product design, right? We come up with the intent and translate that into designs. And based on that, we do new product introduction, certainly develop tools for that. And after that, it's mass production. We rely on provisioning to onboard large number of devices and deliver capacity based on the new product. And then the network is a dynamic system, so we have to operate the network, maintain the network, troubleshoot, to keep the network, deliver traffic in the desired way, and eventually we decommission the product, right? So this is the evolution, iterative process. Provisioning is sitting in a critical place. Certainly we understand it is critical because it delivers massive capacity to the system. But it does more than that in a way that the tools and the components used for provisioning can also be reused in some other places, including network operation. And again, as we mentioned previously, provisioning guarantees that our network is delivered, is provisioned in a reliable way. So it is actually sort of the first line of defense so that whatever we bring into production, we make sure that the problems are surfaced and fixed, and then the product fleet is in a good condition and they can give us reliable services, right? So now, what does the provisioning process look like? So this is a simplified picture. There's no reason to make this super busy and include every single component in an exhaustive way. But it delivers the essence, right? On the, this is left, upper left corner, we have models, right? So for example, we have device models, we have circuit models. And this is the design that can represent the data that we need for every single device. Certainly we have other models as well, and it depends on the business need. You develop models to meet your requirement. And then moving on, when we want to provision or deliver capacity, we describe a small chunk of network we want. So this is a network abstraction. So a network abstraction describes a portion of the network that we need. For instance, we can say we have a two-layer network. There's access layer at the bottom, and then we have aggregation layer above that. There's capacity connections between these two layers. So this network abstraction will describe, say, hey, we need 8 devices at the access layer based on this model. And we need 4 devices at the aggregation layer based on this model. And there's, let's say, 3.2 T capacity between them. The striping rule is full mesh. So this is a very convenient way to describe our intent, right? And then what happens is we have automation tooling to read the network abstraction and translate that into individual devices based on the location, based on other naming convention, based on other rules. We translate that into device data, and we do port mapping based on the striping rules, based on the capacity requirement, and then we create a circuit data in the database. And under the hood, we have IPAM to allocate IP addresses, and we have other logic to do whatever needed. And then eventually, we have a complete set of data in the database. So this gives us the single source of truth. And then the device onboarding, when it comes to device onboarding, everything is data-driven, right? We can install the hardware based on the model data from the single source of truth. And then we can check everything, make sure we have the desired derived everything, they're consistent. Then we grab a device, install the desired OS, apply the desired configuration, do all the health checks we need, undrain the device, and then take traffic. Right? So this is a high-level big picture of how provisioning automation works. And certainly, the green box, or the green boxes on the right-hand side, they're high-level business logic. We certainly need orchestration and automation to concatenate all these things together so that they can be executed in an efficient, reliable way with minimal human intervention. So with that big picture being painted, let's proceed to do a case study. So I will use a single router provisioning as an example to touch on some of the specifics. Hopefully that can shed some light on the technical details. So a single router, let's say we have existing upstream network, we have a downstream network, and we want to add this single router to the production fleet. At high level, we have a few steps to do. We certainly need to create the model data and populate them into the database. We need to install the hardware and make the connections. And then we put a bootstrap configuration into this single router so that there's reachability. We verify everything and then upgrade the OS, apply the configuration, complete health checks, and then we undrain to take traffic. So it's not rocket science. It's just pretty straightforward. But what about the specifics? I talked about model and model data multiple times. So people might wonder what exactly you mean by model data, right? There's no standard for all the business. It really depends on your business need, and then you decide what data you want to have, and then you create models for that, right? And here I list a few commonalities, right? For instance, we may want to describe what hardware we use, including vendor, chassis, line card, transceiver, fabric card, fan, PSU, etc., right? And then we may need models for interface and circuits. So we say what is A end with Z end connections, what is speed, what is port channel, those kind of stuff. And then we have IP allocation. There are certain open source IPAM. We use in-house built IPAM. And we allocate IPs for interfaces. Devices usually have loopback. Some devices have multiple loopbacks. We allocate IPs for those. And there are other places that we may need IPs. And certainly, there might be security requirements, TAC, local credentials, MACsec, ACLs, etc. These are all modeled. And then installation. So again, installation is not a rocket science, but it is a critical stage. It's not uncommon to see that the installation takes time to finish, and the installation, we're humans, the installation may end up with human errors. So the thing is, how do we use tooling to facilitate this process of both installation and verification, right? So again, one key of mass production is to use a single source of truth to help this installation, right? In the model data, we tell what is the location, what is the rack, what hardware to use, and what interfaces to use for A, Z connections. So with all this model data, field folks do not have to worry about incorrect data, right? And certainly using automation, we can even make certain things much more friendly to the field folks to finish their installation. And with this, similarly, we can simplify verification. We can minimize human intervention in verification. Now we have the single source of truth sitting in the database, so that is the desired data. And we can use our tools to automatically obtain the derived data, what's being actually installed. And then compare this to, it becomes much more efficient to identify cabling mistakes and other problems and get them fixed with clear instructions automatically generated, right? So we talked about a lot of building blocks, and we need to orchestrate them together, right? So this is the part we're talking about unified tooling. So instead of writing ad hoc software, pieces of software and try to piece them together, we take a systematic approach. It's an ecosystem. So a workflow is basically a combination of multiple steps putting together to get things done. And we have an in-house built tool to implement, to realize this workflow automation. So the building blocks for this workflow are called steps. Every step, in most cases, is doing a small thing, but does it very well. And we wrote these steps in Python and compiled them into a standalone package. This package can be executed standalone, but in most cases, what we do is we have a workflow engine that orchestrates these steps together and execute these steps in a sequential way and then get things done. All right, so this is the how do we scale from software perspective, from a single small building block, scale up to a system. And of course, as you can imagine, these building blocks, all these steps, workflow steps, they're reusable, all right? They can be plugged into workflow one for certain purpose, and they can be plugged into a different workflow for other purposes. So it's just like Lego pieces. You can build magic based on all these gadgets we already have. And the next step, we have installed the hardware. Now it's time to do bootstrap. What does it mean? Bootstrap means we want to apply a minimal configuration to the target router so that there's reachability. Of course, for different business needs, there might include different configuration in this minimal configuration here. What we do is we only mostly care about reachability. So we have local credential in the minimal configuration. We have hostname DNS management interface default route in the configuration just to make sure that we can log into that device to continue the subsequent operations. The config generation is based on Ginger 2 template, which a lot of folks here are familiar with. And how do we put that minimal configuration into the box? There are two approaches we employ. One is through console, the other is ZTP. Years ago, we only rely on ZTP, but we experienced some problems occasionally on a regular basis, I would say. So people became creative and then introduced another option, which is through console, direct push. So the dependency is smaller and the entire system becomes more reliable. OS upgrade is no stranger. We have an in-house OS image management to store the images in the central repository and also store the metadata. So we use this workflow steps to pull the image to check if the running OS is the desired version. If it's not, then pull an image from the central repository, install, reload, and verify, and then proceed. Config generation and config push is a regular operation, but it's super important. So when it comes to config generation, the good thing is we already have the model data parked in the database, and then we have constructed a collection of Ginger2 templates. So we have a config generation engine running as a microservice to pull the modeling data for a specific desired target device, and then pull the Ginger2 templates, render the Ginger2 based on the model data, and then concatenate all these small pieces together. Then we have a full device configuration. For ACLs, we use Kaporka, and shortly there's going to be another great talk from by our colleague in the other room about Kaporka. And one thing I want to mention is, in the configuration, a lot of secrets, right? Credentials, max keys, etc. So there are secrets. So we want to minimize the exposure of such secrets. So that's why in the configuration being generated, we don't really include those secrets directly. Instead, we put placeholders. And once the config generation done and the config is ready to be pushed to the target device, then we have another service to push that. And that service will grab the generated configuration and then call another service to replace the placeholders with the real credentials or the secret on the fly, and then push the configuration to the target device, do verification, and then fail hard if there are problems, otherwise pass, right? So this is another scalable design where we have a framework dealing with configuration push, but below that is extensible in that by adding different drivers, we will be able to support different platforms. Again, a very scalable system. So after all this is done, we need to do health checks, right? And on drain. Health checks, this is a generic term. Certainly there are some generic checks we want to do, reachability, hardware checks, software checks, and depending on the business need, we may do certain specific checks. For instance, you may want to check MACsec. In certain cases, we want to verify that the BGP sessions are up and running. And in some cases, people may even say, I want to check the prefixes being received and accepted, right? So depending on the specific use cases, scenarios, we have different health checks. Again, the health checks are modularized and they can be combined in different ways to get things done. And after all this, we undrain the device to take traffic. So again, that's the case study. Again, if we come back to the big question, how do we achieve hyperscale in provisioning? The answer is simple. We have to we have to employ automation. However, this is not a one-off effort. There's no magic in it. Mostly, I would say this is a continuous improvement. This is an iterative journey. And also, there's no one-size-fits-all, right? I'm super happy to share our story here. Some of those may apply to other businesses, but not always we can say this is a recipe for all. So to highlight, there are a few things we feel it worked out very well in our story. Data. We take model-driven data, we maintain the data as a single source of truth, follow these principles. They're essential. And whenever we see there's a need to model certain data that can be very rewarding. We do it. For example, for years, we did not model patch panels, right? Usually people say patch panels, they're passive, they're straightforward, right? But later on, we realized that patch panels, when our business becomes huge, then it starts to be a time-consuming process for our field folks to do installation. So we model the patch panel to facilitate cabling. The other part is tooling. Again, this is an evolving concept, right? We have to observe, analyze our business requirement, and then develop tools to address those issues, to automate and facilitate the process, right? One example is in terms of Bootstrap, we used to rely on ZTP only, but we introduced a second option through console. We're able to save a lot of effort from troubleshooting. All right. At the same time, tooling, again, means an ecosystem. We design and develop within an ecosystem. We want to do this in a modularized way. We want to avoid duplication. We want to make sure that the components we develop can be utilized or reused in other places, and the whole system is unified. Minimal duplication, maximum utilization of the artifacts we have developed. So with that, I would conclude my talk. Again, thanks a lot for taking your time, sitting here. It's 40 minutes, and most of people, everybody is still awake. It's impressive. I'll be very happy to take questions, and I hope our story can inspire more conversations, more innovation. We really look forward to talk to you guys and learn from your story as well.
Thank you, Kang-Xi. That was fantastic. Looks like we have some questions online, maybe in the room as well.
Hopefully they're easy.
Yes, two questions online. They're both related to zero-touch provisioning and console. Michael Osman asks if you have an example of the specific issues encountered using zero-touch provisioning that forced you to move into using a console. And then Matthew Peacock, unaffiliated, says, great talk, but it seems like using console access to bootstrap devices adds more complexity rather than less, as you have different console cabling requirements for different devices. Do you have data that shows a concrete improvement in switching from ZTP to serial console access?
Well, it could be a lengthy discussion, but I can share a few things here. The last part, do we have data? Yes, we have data. We're a data-driven company, so that's exactly what we observed is, ZTP has dependency on the upstream devices. So you send out the ZTP requirement, and there needs to be DHCP relay, there needs to be routing needs to be right on the upstream network, and you rely on DHCP server, you rely on the entire process of grabbing the configuration from the repository all the way down to the target device. So there are multiple dependencies in this, and what we, in the perfect world, everything should work, but in the reality, not always. So that's why we observed quite a few tickets from time to time, and that is the data that drive us to pursue the console-based approach. Of course, through console, there's work to do, but we did some investigation and did a POC to justify that this is feasible, and the cost or the overhead we involve is justified, and then it turned out to be very well. So I'll be happy to talk about more details offline.
Thank you. You did answer I had the same question. And I'm Navendu from Extreme Networks. A lot of your presentation depended, and you alluded to single source of truth, right? So could you elaborate on how you maintain it, or how do you construct it, and how do you continue to maintain that as a single source of truth, especially when you are commissioning, decommissioning devices?
Well, it's it's not a simple. There's no simple answer, right? It's like I said, it's a principle. So we have to. First of all, we have to build the infrastructure to enable this. So which we have a very good ecosystem from software design perspective. So from design perspective for the product, we need to identify what data is needed. Are they modeled? If they're not modeled, it's very easy that people have to park this data in ad hoc places, and then that's a violation of single source of truth. So if we identify those needs, then we say, let's model this data and park it in the centralized database. And once that's in, the major problem is resolved, right? So people find, okay, the data is already there, and we have a unified querying system. Then people start to consume that data. They don't have to bother hard code the data or create duplicate the data in multiple places. So that's the super important thing. To have model-based data and keep it in the first place, that solves the problem. Second is there's certainly tech debt. In certain places, we do have duplication for various reasons. In other places, for instance, duplicate data from one database to another database. But we have to deduplicate those things and deprecate the duplication so that eventually things converge to the single source of truth. Of course, it's based on analysis. We identify that there's no need, no hard requirement to have duplication. And there's sort of, depending on the specific case, there might be migrations to do and make sure everything converges to the single source of truth in a seamless way. So depending on the specific case, we may have different solutions for that.
Thank you.
Thank you.
Okay, thank you again, Kang. That was great.
Thank you.
Thank you very much for your contribution.